In this video, we're going to learn how to name alkenes. In the beginning of this video series, we learned the different functional groups, and we specifically noted how, in the case of alkenes, they have carbon-carbon double bonds. In the case of alkynes, they have carbon-carbon triple bonds. The general formula for alkenes is CnH2n, where N must equal starting at 2 up to infinity. And then in the case of alkynes is CnH2n minus 2, where N starts also at 2, and it continues on to infinity. When it comes to alkenes and alkynes, they are called unsaturated hydrocarbons because they do not contain the maximum number of hydrogen atoms that a carbon atom can hold. An example specifically for an alkene is lycopene. Lycopene, which you can see its structure on the right side of the slide, is an important antioxidant that it is found in red fruits and vegetables. And for example, in tomatoes, the red color that that fruit has comes from this structure, which is known as lycopene. Let's now learn how to name alkenes. The rules for naming alkenes, we can see them illustrated specifically on the left side of the slide. Step number 1 states that you're going to find the longest continuous chain of carbon atoms that contains the carbon-carbon double bond. You're going to write the alkane name, but then you're going to change the ending from A-N-E to E-N-E, because when we're naming alkenes, the names end in "ene." Next, in step 2, we're going to number the carbon atoms starting from the end that is nearest to a double bond. Now, we're going to see in the second example that if my double bond is equidistant, meaning that in either direction that I number it, the carbon-carbon double bond has the same numbering, then we must select the number that is closest or that is at the beginning of the first substituent or near the first substituent that we have here. Only then. Next, we're going to give the location and the name of the substituents as a prefix of the main chain. We also need to give the position of the first carbon in the double bond preceding the name of the parent chain. Let's go through both examples that we have in the following slide. Here is our alkene. First, we need to identify the longest carbon chain that contains the carbon-carbon double bond. So in this molecule, you can select carbon 1, 2, 3, 4, 5, or carbon 1, 2, 3, 4, 5. It will result in the same name, regardless of which one of the two longest carbon chains that I illustrated right now. Let me number them. 1, 2, 3, 4, 5. And the reason why I number it in this way is because remember that in rule number 2, it tells you that you need to number from the end that is closest to the double bond. You only do it from the substituent point of view when you have an equidistant alkene. So since I have 5 carbons in my longest carbon chain, let me highlight them. Carbon number 1, carbon number 2, number 3, number 4, number 5. The alkane name for this is pentane. But since this is an alkene, I'm going to take the A and E ending and replace it by E and E because we have an alkene. I need to put as a location the first carbon in the carbon-carbon double bond. So that means that at carbon number 2 is where my double bond starts. And then I'm going to write the location and name for the substituent. For this molecule, at carbon number 4, we have a methyl group. Remember that every time we have words and numbers, they are separated by a hyphen. Let's look at the next example. This is an example of an equidistant alkene, and let me illustrate why. If I number this alkene 1, 2, 3, 4, 5, 6, or 1, 2, 3, 4, 5, 6. It doesn't matter it doesn't matter which direction I do the numbering, because in either direction, my alkene has not only 6 carbons, but the carbon-carbon double bond is in between. Carbon number 3 and 4, you can see it in any direction. Only then the numbering that stands is going to be the one where it starts closest or nearest the first substituent in this molecule. So in this case, the blue numbering is the correct one. Since I have 6 carbons in this alkene, that means that the name for the parent is going to be hexene. The first carbon in the carbon-carbon double bond is 3. And I have a substituent on carbon 1, which it is a fluoro group. Please do not forget that between words and numbers, there's always hyphens. Make sure that you continue to practice with the in-class worksheets that are provided to you. You need to be able to draw condensed and skeletal structures for alkenes. Let's do as an example the number 1 name that we have there. We have 3-ethyl 1-pentene. Similar to how we learn how to draw alkanes in the first set of videos, let's now do the same exercise, but with this word. The first thing that you're going to draw is the last word. Pentene tells me that my longest carbon chain is going to be 5 carbons. 1, 2, 3, 4, 5. I'm drawing the condensed first. The 1 before the pentene tells me that between carbons 1 and 2, that's where my double bond is. In this case, it's right here. That's between carbons 1 and 2. On carbon number 3, specifically, I have an ethyl group. An ethyl group is written as a CH2, CH3. Then I fill in my hydrogens. Starting from left to right, the first carbon gets 2 hydrogens. The next one gets 1. The next one gets 1. The next one gets 2. And the last one gets 3. Make sure that you practice and you do not exceed the 4 bond rule that carbon has. If you exceed the octet, understand that your structure will be marked incorrectly. What about the skeletal structure? How do we draw that? Well, similar to what we learned before. When I put my utensil on my paper or wherever the surface that I'm writing my answer, that's carbon number 1. Then I go up, carbon number 2, down, carbon number 3, up, carbon number 4, down, carbon number 5. My double bond is in between carbons 1 and 2. So I draw a line between the first 2 carbons. And then to draw my substituents, I count carbon 1, 2, 3. And on carbon number 3, I do a bond and a bond. So these two represent the CH2CH3 that I see in the molecule. Make sure that you practice. Now, alkenes specifically, because of their electron group geometry, are known to be rigid and that they do not rotate in terms of the flexibility that maybe other electron group geometries have, for example, tetrahedral. So alkenes actually hold their substituents in fixed positions, which makes them have different structures, which are known as cis or trans isomers. So let's take the example that we have on the slide. Here we have, like if we write it from left to right, we have 1,2-dichloroethene, but those 2 chloro groups on the carbons in dichloroethene can be both pointing on the same side, meaning pointing both up or both down, and that is known as a cis configuration on your alkene. Another way that you can do cis is by writing the letter Z. And that's because there is a German word that means the same sides that starts with a Z. Sorry, I don't know how to pronounce it. But sometimes instead of cis, you see the letter Z for that German word. And it also means cis, meaning that those substituents are pointing to the same side. If the substituents are not pointing to the same side, you can see them that they can be up pointing towards opposite sides, meaning one is up and one is down. That is known as a trans isomer for an alkene. And there's also a German word that represents opposite sides. I don't know how to say it, but instead of trans, sometimes you see the notation E for alkenes. So E means trans. As part of naming, you guys need to know for alkenes specifically, because this phenomena only happens in alkenes, how to identify if the alkene that you're naming is cis or if it's trans. Let's proceed to do an example. Here we have the following alkene. Take a moment and name it before we assign the cis versus trans isomerization that they have, or the isomer designation, I should say. So finding the longest carbon chain, I hope that you were able to find that this is 1, 2, 3, 4, 5 carbons in length. So the name of this alkene specifically is going to be 2-fluoro, 2-pentene. Now, this molecule, we can determine cis and trans, and this is how you proceed to determine, is this a cis or is this a trans? First thing you have to do is envision that we have to cut, let me use a different color, this molecule in half right at the double bond. Next, you are going to determine what are the designations for the substituents on the left side of the double bond versus the right side of the double bond. Okay, let's deal with the left side first. Carbon number 2, which is right on the alkene, is connected to a fluorine versus a carbon. Because remember that even though this is skeletal, this is representing that there's a carbon right here and it has 3 hydrogens. So carbon number 2 is either connected to a carbon versus a fluorine. So how do we decide, how to designate, who gets priority for this same side, opposite side thing? You need to determine it by looking at the atomic number for the atom that is connected to a carbon in the double bond of an alkene. So carbon number 2 is connected to fluorine versus connected to a carbon. Fluorine has a higher atomic number compared to carbon. So that means that fluorine, we are going to give it a high label because of its higher atomic number compared to carbon. So carbon is going to have a low designation because it has a low atomic number compared to fluorine. Let's now move on to what's happening to the right side of that carbon-carbon double bond. So on the right side of that carbon-carbon double bond, this is where it lives, here we have a CH2 followed by a CH3. But carbon number 3 is directly attached to a hydrogen. So essentially on carbon number 3, what we are comparing is the attachment of carbon number 3 to another carbon atom versus carbon number 3 connected to a hydrogen atom. Take a moment, look at the periodic table, determine which atom has the high atomic number versus the low atomic number when we are comparing the atoms directly connected to the carbon in the carbon-carbon double bond. You should have observed that carbon has a higher atomic number compared to hydrogen. So we labeled them. Well, compared to carbon, hydrogen is a low atomic number, and this is high atomic number. Now, if we look at our molecule and we look at the designation of high and low, you can notice how the high and low designations are both towards the upper side of the molecule in that alkene, and the low are on the same side. So that means that when we look left to right across that alkene, since the high and low designations are pointing towards the same area, in this case, the highs are pointing towards the upper part, the lows are pointing towards the down part. Since they are pointing towards the same direction, that means that this molecule or this specific alkene is cis. In other words, is going to be Z2-fluoro 2-pentene. Either name is correct. Take a moment and determine what is the name for the following alkene. This alkene has 1, 2, 3, 4, 5, 6 carbon atoms. Its name is going to be 2-bromo, 2-hexene, if we try to determine cis versus trans, got the molecule right here. This is a low priority group. This is a high priority group. Carbon number 3, there's a hydrogen. That is a low priority group. This is a CH2. This is a high priority group. And remember that that high and low, I assigned it based on atomic number. We can observe that the highs and lows are pointing towards the same direction. Both highs are in the bottom, both lows are on the top. So that means that this is also a cis, meaning Z, 2-bromo, to hexene. Let's do at least one more. Take a moment and name the following alkene. For this alkene, this is 3-methyl, 3-hexene. When I determine if this is cis versus trans, this is how I perform it. I cut the molecule right here. On carbon number 3, that is connected to a carbon with 3 hydrogens. This is connected to a carbon with 2 hydrogens. This is a carbon with 3 hydrogens. Carbon number 4 is directly attached to hydrogen, while carbon number 5 is a CH2, and this is a CH3, okay? So let's now designate the high versus low. On carbon number 3 is directly attached to carbon and attached to carbon. Now, those carbons don't have the same atoms, because we can see that this has 2 hydrogens and a carbon, and this has 3 hydrogens. Since this group that is pointing down has a higher atomic number because of this carbon, this group is going to be the high priority group. Let me illustrate that a little bit further so it's more clear. If I make the list of atoms that is connected to this direction on carbon number 3, I have a carbon atom, meaning this one, that is connected to 2 hydrogens. This carbon atom connected to 2 hydrogens is also connected to a carbon. If I look at the one pointing in this direction, I have a carbon atom connected to 3 hydrogens. When I look at those atoms, I need to find a point of difference. Carbon and carbon, no point of difference. Hydrogen and hydrogen, no point of difference. Hydrogen and hydrogen, no point of difference. So that's why I mentioned that this atom is what determines the difference, because the one on top has 3 hydrogens. So when we compare hydrogen to carbon, then This has a higher atomic number compared to one of the hydrogens here. So that means that when it comes to prioritization or priority, this is a high priority group. This is a low priority group. The atoms that are connected to carbon number 4, I'm comparing hydrogen to a carbon. Hydrogen is also a low priority group. Carbon is a high priority group. In this instance, we also observe that this is a cis molecule because the highs and lows are pointing in the same direction. Take a moment and determine if the following alkene is cis versus trans. If you determine that this molecule is trans, or in other words, E, you're correct.